Hi, my name is Jasper, and I've been doing research on identifying outliers in galaxy data. Traditionally, galaxies have been classified into three types based on their observable shape. There's irregular galaxies, elliptical, and spiral galaxies. Spiral galaxies are characterized by their spiral arms, and they eventually grow into elliptical galaxies when the stars in them get older and the gas and dust used for star formation are used up. And irregular galaxies usually only happen in outlier cases when, for example, two galaxies collide. Another way is now used to classify galaxies, which is their spectral energy distribution. A spectral energy distribution of a galaxy is just a graph of their flux on the y-axis versus either their frequency or their wavelength on the x-axis, and it looks something like these graphs. It was outlined in this paper that when you get certain data points on this graph from observational studies, you can oftentimes fit the entire graph to guess what it would be like.
Spectral energy distributions are very important to the understanding of galaxies, and we can also understand them through looking at their color. Photometric surveys will have filters to only let through certain wavelengths of color, so that when we get color data, we will know the color index, which just says what color the object we're looking at is, and usually that also determines the temperature. And we also get redshift data, which tells us how fast it's moving away from us. And for my analysis, I looked at 3 different redshift bands. I looked at 3 different colors. So if you look in the spectrum, we had U minus B, B minus V, and V minus J for the 3 colors. What we use for this analysis is the Cosmos 2020 survey. It's a photometric survey as opposed to a spectroscopic survey, which is usually focused on, for example, like a particular galaxy or a particular star. This is a wide survey of a portion of the sky, and it had a bunch of telescopes pointed at it, and their filters recorded at different colors the intensity of light. So this is the code I wrote. I wrote in Python. What you have to do is there's this FIS file that you get from the Cosmos survey, and you open it using various libraries like AstroPy, and you extract the data. I cached it into CSV so that I wouldn't have to redo that entire thing every time. And then I trained the model using scikit-learn, that's basically these 3 lines, and then plotted using matplotlib to generate the plots that you'll see on the last slide.
The algorithm that I used here is called the local outlier factor algorithm. It's an unsupervised machine learning algorithm that's trained on the data we give it, and it determines which data points are outliers. So the way it works is for each point, it calculates the density of that point using the reachability metric, which just compares, it's based on the distance between the point and its 20 nearest neighbors, and the distance between the neighbors and their neighbors. And it uses that to calculate that if the metric is above a certain threshold, then the point is considered an outlier.
So these are the results of the analysis. The data is shown here. We have 3 redshift bands from 0.2, 0.25, 0.97 to 1, and 2.9 to 3. And there are 3 properties of each. You have the stellar mass, the star formation rate, and the specific star formation rate, which is the mass of the stars that are formed. The trend is that in the outliers, the values are greater than they are in the non-outliers, except for the specific star formation rate, in which they are about equal. I analyzed this data for 10 outliers as well, and I found that there's a stronger shift towards the outliers being the numbers being bigger, even for the specific star formation. These are the results in graphical form. You can see in the mass and the SFR case, the blue is shown above the red, and for the specific star formation rate, it's very similar.
So there are some next steps that could be done to further the results of this. We could look at more colors for each galaxy than just the three that we looked at. We could also look at other physical properties other than mass, star formation rate, and specific star formation rate.
That's all I had. Thank you.